Hello, welcome back to System Dynamic class. This is Practicum Module 5 entitled as DC Motor Simulation. In this practicum, we are going to simulate two types of DC motors, which are field control DC motor and armature control DC motor. This is the field control DC motor. The field consists of a resistor of RF that is in series with an inductor of LF. This field is going to be driven by an external voltage that is VF, and as a response, there will be current flowing on the field denoted by IF. On the other hand, we have an armature that is injected by a constant current of IA, and the armature itself is connected to a load, and as a response, we will have theta and omega. Theta is the angular position of the shaft in radian, and the omega is radian per second. This is the angular speed of the shaft. This is the entire model of the motor we have derived in the class. There are two inputs for the motor, which are the voltage being applied on the field and the disturbance. As the output, we will have omega as well as the theta. These are the parameters of the motor we want to simulate. The simulation will be conducted in MATLAB, where the disturbance is assumed to be Td as a function of time, that is equal to 0.5 sine 2 pi t. The unit is Newton millimeter. The output of the simulation is to obtain the plot of omega against time and the theta against time for each input. We have 5 different inputs. The first one is 1T, which is unit step, which means that the voltage is maintained constant as 1 volt. And for the second one, step function plus sinusoidal function with amplitude of 0.1. This one is step function that is stepping when t is equal to 0. And this one is another step function that is stepping at t is equal to 5 seconds, and so on. Okay, let's start with this. Let's start the simulation using MATLAB. Here, firstly, I'm declaring the entire parameters of the motor: the resistance, the inductance, the Km, motor constant. This one is the moment of inertia, and this one is the torque coefficient. And then I'm declaring the time started from 0 up to 10 seconds with step size of 0.01 second or 10 millisecond. And this is the input. We are going to vary. The first one is, remember, the first one is step function, unit step function. So I'm declaring a matrix with all members is equal to 1, and the size of the matrix is exactly the same as the size of the T. And this is the disturbance of the disturbance we apply on the motor. The amplitude is 0.5. Be careful. I'm applying E minus 3 here since the unit is in Newton millimeter, not in Newton meter. Okay, and this is the sine function. This is the S. What I'm doing here is declaring the Laplace variable, that is S. And G1 is the transfer function of the motor correlating the omega and the voltage. As you can see here that the omega is correlated with VF by these three transfer functions. The field, that is 1 over RF plus LFS. The second transfer function is Km, and the last one is 1 over Js plus F. So what I'm doing here is I'm multiplying this all, thus I get G1 is equal to this one. Okay, so this is the multiplication of those three transfer functions. And This is the main simulation we conduct in MATLAB. The main program of this practicum. This is LSIM. Yeah. LSIM stands for linear simulation. So omega 1 is the rotational speed of the motor that is caused by Vf. So Vf is the input. G1 is the transfer function correlating the Vf and omega. Okay, and for the last one, we put matrix T here. And then secondly, I'm declaring G2, another transfer function. It correlates the torque of disturbance, and the omega. As we can see here, that the omega is correlated with the disturbance by this transfer function. So G2 consists of this transfer function only. Okay, this is 1 over Js plus F. And omega 2 is the omega that is caused by the TD. Okay, so this is linear simulation. The transfer function is G2, the input is TD, and this is the matrix of time. And totally, the omega experienced by the shaft of the motor is omega 1, which is omega that is caused by the voltage, minus omega that is caused by the disturbance. And then if we want to find the theta, what we do is we perform another linear simulation with transfer function of 1 over s. This one is 1 over s. And then the input is omega, and we always put matrix of time here. If we are going to investigate how the IF appears, we can do the same thing by executing linear simulation. The input is 1 over LFS plus RF. The input is VF, and this is matrix of time. Okay, so the IF is the input of this transfer function, and this is the input for the transfer function. So that's why I'm writing the transfer function as 1 over LFS plus RF. Okay, so that's all the simulation. Now, I'm plotting the omega 1, omega 2, and omega on the same plot. Line with 2, I'm making the line thicker than usual. Grid on is to turn on the grid, and legend is made to distinguish this all. Omega 1, omega 2, and omega t. Okay, let's see how it results this simulation. Okay, we have got the result. So this is omega 1. Omega 1, the blue one is the omega that is caused by the voltage. The red one is the omega that is caused by the disturbance, and the orange one, the orange line, is the total omega 1 minus omega 2. Okay, so this is the response. The real response of the motor is something like this. Okay, we perform the simulation for 10 seconds. I don't think that it's enough, so we can customize the length of the simulation up to, let's say, 40 seconds. And then I'm running the program again, and then this is what we get. Okay, so this one is the it belongs to omega that is caused by the voltage. The red one is the omega that is caused by the disturbance, and the yellow one or the orange one is the total. If you want to plot the current on the field, all we need to do is just replacing this all by I underscore F. Okay, and then I'm running this all. Oh yeah. Okay, so this is the IF. This is the current on the field. Yeah. I don't think I need the legend. I don't need the legend. Yeah. So I'm adding this comment sign by percent. Okay, so this is the current on the field suddenly increasing here. Okay, so this is the simulation. Yeah, we have done. Yeah. Okay, so now let's try for another input. Yeah, for the second simulation, the input is unit step function plus 0.1 sine 2 pi t. So here we can customize the input by adding another function which is 0.1 multiplied by sine 2 pi t. Okay, so this is the input voltage, and then let's see how the omega appears. Yeah, okay, so this is the result. Yeah, let's see. uh, let's see this closer. Okay, so this is the comparison between the omega 1 and the omega. Yeah. Okay, number three is this is a step function, and this is another step function, but it is delayed for 5 seconds, which means that this one is stepping at t is equal to 5 seconds. So what we do here is that, so I'm going back to the original one. This is VF. Yeah. Okay, so this is omega 1. Yeah. So I'm declaring this, I'm changing this as omega 1A, right? Okay, and then I want to find, yeah, omega 1B. Yeah, omega, so it produces omega 1A, it produces omega 1B. I'm separating the simulation into two. Yeah. Okay, so this one is G1. As the function is delayed as 5 seconds, so what I'm doing here is multiplying this by an exponential function minus 5 multiplied by s. Okay, so remember that delaying the function in time domain means that we are applying the transfer function with an exponential function where the constant is exactly the same as the delay. Okay, and the omega 1 is equal to omega 1a minus omega 1b. Yeah, okay, why minus? Because uh, this is subtraction, not addition. Yeah, this result minus this result. Okay, so I'm running this. Okay, so this is the response. Yeah, the blue one is omega 1, the red one is omega 2, and the orange one is the omega or the total. Okay, now number 4, this is 1t plus sine signum function of sine function. Yeah. Okay, so actually I can do this. Okay, let me separate this. This one is okay, yeah, let me do this. This is omega 1. Okay, so I'm customizing this as, yeah, okay, so I think this is the original one, the first one, and then plus sine of sine 2 pi t. Okay, so let's see what. Okay, so this is the response. Yeah, maybe you ask me what signum function is. Let's see. Help. Okay, let me show you this. Sine of minus 0.0001. So for every negative number inside this bracket, the function results in minus 1. Yeah. Okay, so if this one is negative, then the result is minus 1. If this one is positive, this one will be +1. Okay, so for example, I'm changing this as positive, something, any positive number inside the bracket, then it results in 1. Yeah, so the output is just -1 or 1. Okay, what about 0? Let's see. If this one is 0, the sign is 0. Okay, so okay, let me show you how it appears. Yeah. Okay, the t is, I'm declaring the t. Yeah, the t. Have a look. Yeah. So I'm okay. This is up to 5. X is equal to sine 2 pi t. Okay. So this is ordinary sinusoidal function, and the y is signum function of x. Okay, now I want to show you. Yeah, okay, let me close all first. Yeah, I want to show you how they appear. Yeah, t comma x comma t comma y, grid on. Yeah, and then y limit is the limit of y-axis is from -2 up to 2. Then okay, so have a look. This is sinusoidal function, and this is signum function of the sinusoidal function. So it creates a rectangular signal, something like this. Yeah. Okay, and the last one we are going to simulate is ramp function. Yeah, rt is equal to okay, it is simple, very simple. Yeah. It is equal to t. Yeah, so it is increasing, it increases as the time passes by. Yeah, with slope of 1. Yeah, this is the slope of this function is equal to 1. Okay, let's see how is the result. Okay, so this is the result. Yeah, okay, let me show you omega only. Yeah, omega only, something like this, and then okay, so this is the response. Yeah, this is the response when the input is ramp function. Now again, I'm separating the simulations into 3 parts. Yeah, so this is the first part. It will be the second, and it will be the last. Yeah. Here, the omega 1 is LSIM G1 VFT. Okay, I think it will be omega 1A, right? And then I'm creating another one, omega 1B, right? This is 2 times, so I can put the 2 outside the simulation because this is just a constant, and the function is just the same as a ramp function, but it is delayed as much as 5 seconds. So what I need to do here is that multiplying this by minus exponent of minus 5s, right? Okay, the input is still VF, and then this is 1 omega 1C. Yeah, the slope is 10, so I put a 10 here. Yeah, the delay is 10 seconds. Yeah, so I'm changing this by 10. Yeah, and finally we have omega 1s, omega 1a minus, yeah, have a look, this is minus omega 1b plus omega 1c. Yeah, that's all. Yeah, I think it's already complete. Okay, so this is the result. Yeah, okay, this is the result. Okay, so we have done this all, and the last simulation is for armature control DC motor. Yeah. For armature control DC motor, yeah, there is something different, yeah, which is back EMF. This back EMF is produced by the omega. Yeah. As the omega increases, the back EMF increases. Yeah, so it is proportional with the speed. And then the way we obtain the back EMF is a constant, back EMF constant multiplied by the omega. Yeah, that's all. And then this is the Km. Yeah, this is the Km. This is the Kb. This is motor constant. This is back EMF constant. Yeah, that's all the difference. And then let me show you. This is the armature. Yeah. Let me show you that. Yeah. Firstly, I'm declaring G1. Yeah, have a look. G1 is Km LAS plus RA divided by JS plus F. So what I do is this omega is equal to VA multiplied by this transfer function multiplied by this transfer function Km multiplied by this transfer function. But we have to include this effect. Yeah, this effect is included by, so actually the this G1 valid only for field controlled case. Yeah, for this case we have to include this. Thus what we do is I'm declaring G11. G11 is feedback, yeah, G1 comma KB. Okay, so this is obtained by G1, and then there is a feedback, and the transfer function on the feedback is KB. So I put KB here. Okay, so G11 is the transfer function we will use for the linear simulation. Yeah, so omega 1 is LSIM, linear simulation. The transfer function is G11. Be careful, this is not G1. The input is VF, and this one is T. Similar to that, yeah, I'm declaring G2, this correlating the omega and TD, but we have a feedback. Have a look, this is the feedback. The feedback will be KB multiplied by the armature transfer function and the Km. So yeah, I'm here. This is G2 1 over JS5F, and then feedback G2 comma KB multiplied by Km. Yeah, so I need to make it complete, Km. Yeah, and then divided by this one. Yeah, divided by LAS plus RA, something like that. Yeah, and then the omega 2 is the omega that is caused by the torque. Linear simulation, the transfer function is G22, the input is torque of disturbance, and this is matrix of time. And totally the omega is omega 1 minus omega 2. Yeah, and then let's see how it appears. Okay, this is the effect, the result. Okay, good luck. So please for the armature control DC motor, please do similar simulation with various armature voltage. Okay, so previously we performed 5 different simulations with different voltage applied on the field. Yeah. And for this one, for armature control, you have to apply, yeah, this 5 voltage that is applied on the armature. Okay, good luck. Thank you very much, and see you again.